Good morning, everyone. Good afternoon. Welcome to our panel on Advanced Catheter Manufacturing. My name is Barry Schnur. I'm the CEO of David Schnur Associates, and on behalf of the DSA team and our partners, I want to thank everyone for joining us today. But for today, we wanted to provide some meaningful technical discussion on new materials and processes for interventional delivery systems. As many of you know, this has been a core focus of David Schnur Associates for over 40 years. And I'm going to take a few minutes to introduce our panel, some of their core technology focus, and how that fits into our topic for today. Now onto the panel, an accomplished international group. Let me start with Dr. JOCHEN ULMER of Euroflex. Based in southern Germany, JOCHEN is a nitinol metallurgist and the vice president of Euroflex. In the 10 years that we've worked together, JOCHEN has been directly involved in everything from next generation implant materials to the development of Euroflex's unique catheter quality manufacturing capabilities in Costa Rica. Euroflex itself is the medical arm of GRAO Inc., a 140-year-old privately owned metals company that has quietly led the development of nitinol tubing materials for decades. Today, we are going to be focusing on changes that have made nitinol tubing a more compelling option for catheter inner members. We'll also be talking about the inherent properties of the metal, capabilities for making components, and of course, mining JOCHEN's extensive knowledge of the processes that lead to differential properties. JOCHEN, thanks for joining us today.
Sure.
Next, I'd like to introduce Robert FOLEY, president of Cobalt Polymers in Northern California. In the 25 years that Robert and I have known each other, I've seen him creatively approach a wide range of material and technology problems by creating small, focused operational and engineering teams. With Cobalt, FOLEY has created a unique portfolio of thin-walled, flexible heat shrink tubes that are specifically optimized for interventional devices. Cobalt Polymers' introduction of PEBAX heat shrink to the market 10 years ago really put the company on the map and has continued to drive their success as a global supplier to the medical device industry. In our discussion, we'll focus on how PEBAX heat shrink and heat shrink generally can best be used in wire and tubing-based interventional devices, and talk about how to use the properties of the materials to create some really incredible structures. Robert, thanks for joining the panel today. Next, we'll head to England and welcome DARREN Vine with XL Precision. DARREN has about 20 years of experience focused on metal tubing, extrusion, and forming, using a range of processes, alloys, and materials before he joined XL a few years ago. XL is the new kid on the block as a DSA partner, but we've known them for quite some time as a dominant force in English micromachining. With their expansion into Pennsylvania, it became an interesting match for us in key markets. XL blends a core competence in EDM with laser cutting and welding, conventional micromachining, and metal 3D printing to create a whole range of complex structures. Today, we'll be focusing primarily on what can be achieved using laser processing of thin-walled hypotubes, and then exploring some of the options for combining additional technologies in these components. It's been a great pleasure to start working with DARREN. I appreciate your joining us today.
Thank you, Barry.
Finally, it's my honor to introduce Ryan BALKO with Nordson Medical in Minnesota, a biomedical engineer at Fast Forward, Invention Medical, where he served as engineering manager before taking on a commercial role. Ryan leads Nordson's engineered shaft business unit that includes design, development, and manufacturing of interventional catheters. One of DSA's oldest partners, Nordson Medical provides a tremendous range of device solutions, ranging from unique tubing materials and components to complete medical device manufacturing. Today, we'll be focusing on how you can utilize modeling and other systems to reduce development cycle times in shaft R&D. We'll also talk in some detail about Nordson's experience in pushing the limits of traditional braid and coil reinforcement technologies, while also incorporating the other materials that we're going to be discussing today. I'm particularly interested in hearing the panelists talk about the relative merits of these approaches and how complex materials and processes interact in the creation of advanced devices. Ryan, thanks for joining us today.
Thanks for having me.
Absolutely. I hope that's provided a little useful context. Now for some details. Let's start with Dr. ULMER. JOCHEN, thanks again for joining us. We're going to be talking primarily about catheter quality tubing amongst the whole range of nitinol capabilities. Can you talk just quickly and explain what we mean by catheter quality nitinol tubing?
Yeah, so thank you, Barry, for the invitation to talk about that today. So yes, there are differences in how nitinol can be processed, and especially for tubing, there are two different kind of, I would say, families of nitinol tubing. One is more for, let's say, the stent and the heart valve direction, which is mainly driven by OD and wall, or OD and ID wall tolerances. And on nitinol catheter tubes, it's more the ID and OD tolerances which plays a big role. That's from the perspective of dimensions. That's what's driving it. And the other thing is that you typically want to have long pieces. So one way to do that is kind of having continuous processes to make those tubes and to make them suitable for long pieces you need for catheters. And on the other side, have a cost-effective way of production and make them available for catheters, because it's not a multiple use or an implant, it's a single use instrument typically. So cost plays a big role.
Great. So generally, what applications are best suited then for catheter quality tubing?
So I would say, I mean, anything typically which is, let's say, what we call the over the wire catheters. So where you have let's say an inner tube where you push the guide wire through, and you have an outer tube where you put the pressure through for let's say, for example, blowing up the balloon. And to make that flexible and to make that kind of to make that stiff enough and flexible enough to go around the curves, nitinol is a very good let's say material to do that, because we don't go that far deep into nitinol today, but one of those capabilities is those let's say the industry calls super elasticity. So you can bend it very far, and it comes back to the original shape once it's released, and that gives it that's a great instrument you can use for catheters, because there you have to go through very small curves, radiuses, and you don't want to. What you don't want is that the catheter is kinking on its way, and that's what you can realize with nitinol catheter tubing.
No, I think it's a great point. I mean, there are certainly off-the-shelf materials or kind of generally specified nitinol materials, but they can be highly tuned as well, even before you go into custom alloys or differential materials.
I mean, what we're offering, we have an extensive stock list where, let's say, if you want to start with a certain project, you can just let's say pick something off the stock list to get started. And once you're clear what kind of dimension and what kind of properties you need, then you can have then we can make a custom run. And by that, you can really cut down your development time quite a bit if you start with what's available on the shelf. Perfect.
So I think, you certainly hinted at this, but nitinol is considered, obviously, and is for implants, an expensive material to use. What is the key differentiation in terms of, an advance in terms of the manufacturing process that leads to this less expensive catheter quality tubing that you can use in longer lengths?
I mean, of course, one way to bring the cost down is, yes, of course, first of all, that's true. I mean, nitinol is a little bit more expensive than stainless steel. On the other side, you can do designs with a nitinol tube you can't do with stainless steel. And we mentioned about the kinking already. Right. But one way to make it effectively is kind of do it in a continuous process. And by that you can really dramatically kind of cut the cost down but of course you pay with tolerances on the wall, but that's typically not what is important for a catheter typically. I mean, it's more important for stand quality.
Very good. Yeah, and I think the final piece, I talked about the facility in Costa Rica and having been there, and I think this is unique in Costa Rica of having that kind of advanced metals processing facility. You had pointed out to me that it's not really the difference in the cost of labor, but the equipment itself, given that it's automated and continuous process. That's really the impact.
I mean, we see a growing demand on nitinol tubing worldwide, and that's why we put an additional manufacturing plant into Costa Rica, because it's a great place to be there. I mean, there's great labor there, they're great people, and they're very high quality in what they can make there. So we don't see any differences, quality difference between our German facility and the Costa Rican facility. So it's, but the positive thing is we are closer to our customers in the US. That's a very important point for us, of course.
Very good. Thanks. We'll come back to Euroflex on the panel. I had to Ryan for a minute. Ryan, let's talk about Nordson Medical.
Yeah.
So first, can you, you're based in Brooklyn Park, and this is, kind of the core facility, right, for Nordson's engineering shaft and interventional products. Can you give us a quick overview of the complex engineering shaft capabilities there?
Yeah, absolutely. For those of you that don't know Nordson Medical, we do have 15 facilities located globally, really focused on design and development and integrating our component technologies into finished device solutions for our customers. Primarily focused on balloon catheters and complex engineered shafts. So we do have our Center of Excellence for Domestic Manufacturing located in Brooklyn Park, Minnesota, but we also have established development centers located globally to support these types of systems. Very recently, we've invested heavily in building out our quick turn capability specifically for complex engineered shafts. And we opened a new office in Louisville, Colorado to support exactly that, to respond to our customers' need for getting prototypes in hand quickly. Across all of our facilities that support these types of systems, we have all of the necessary catheter manufacturing capabilities, from braiding to coiling to encapsulating laser cut hypo tubes, RF tipping, handle assembly, handle design, as well as all of the component capabilities to allow us to have kind of industry leading vertical integration in this space. So we have capabilities for both film cast PTFE liners, ram extruded PTFE liners, FEP heat shrinks, thermoplastic extrusion. So really the full gambit of whatever's needed to be able to support complex engineered shaft and delivery system development and manufacturing.
Ryan, beyond the quick turn and kind of general overview, I wanted to talk about how Nordson capabilities and what you've done can really minimize R&D cycle times. Because development of complex shafts, I think typically multiple passes in terms of getting to a final design. How have you guys been using this SimShaft modeling, and what's the impact on prototyping?
Yeah, we use it very commonly, and especially in early stage development. If you're not familiar with our SimShaft offering, it's essentially a quantitative software package where it allows us to input certain design configurations of composite shafts, whether that be one layer for looking at how a single extrusion might operate, or multiple layers for how a composite shaft might function in terms of performance. So it's a great tool for kind of baselining and benchmarking a starting point for where we're looking at for development, and then allowing us to build up multiple iterations, making tweaks. Might be different coil patterns, different wires, different braid patterns, different number of starts for braid wires. Input all of those different variables and get kind of a computational output that gives us a directionally accurate starting point for jump starting development. So it's a very useful tool for helping to kind of down select if there's, our customers come to us with a list of design inputs. It allows us to help kind of narrow that funnel down from, a huge quantity of potential options and variables to be pulling at, and kind of guide the initial development in the right direction. So it's a very powerful tool for helping us to at least get the program started in the right direction. It is a computational software, so it doesn't have direct correlation to what your actual outputs will be for kink resistance or tensile strengths or compression resistance or torsional rigidity or any of those types of performance features, but it is very powerful for giving us a great starting point.
Can you talk about how this figures into, for instance, steerable design? Somebody comes in, is it sophisticated enough that it will help you actually reduce design cycles for steerable shafts?
Absolutely. Really, the way we can carve it up is we can chop each individual segment of the catheter into a standalone piece and look at how that will perform if we change different design features and play with those variables. So it's definitely very, very helpful in the complex shafts when we're trying to tackle complex problems. So yeah, we use it for anything from micro catheters to standard cardiovascular guide catheters to complex structural heart type applications. So there's really no limitations to where we can deploy the technology.
Fantastic. Well, thanks. Robert, thanks for getting back with us.
You're welcome.
All right. So back to heat shrink. How can you walk us through how the use of PEBAX heat shrink might compare to a reflow process to get a PEBAX jacket onto something?
Sure. In a standard reflow process, you've got your substrate, but then you've got to size your PEBAX accordingly to your substrate, and then your FEP jacket over that, and then all of that is recovered down, and then the FEP jacket is skived off. You're limited as far as your diameters that you can use because of that very limited shrink ratio that you have with FEP versus just taking a piece of heat shrink, sizing it up to your substrate, applying the heat, recovers down, and it moves on to your next process. So a very streamlined, quick process versus the reflow.
Okay, and we're talking for sure about catheters today. We've also hinted with at Nightingale with some others. Some of the pictures you have up are of hypotubes, and others are of wires. Can you talk a little bit about the use of a thin jacket and sort of what are the quick diameter limitations? How thin of a PEBAX wall are we talking about?
Yeah, depending on length, we're down sub ½ mil on walls on our PEBAX. We generally stay up anywhere 5 to 6 thousandths is where we like to top out at, but we've gone up to 10. But with that, you've got greatly increased flexibility and toughness by having a cross-linked PEBAX on there. And with an extremely thin wall like that, it'll open up that envelope that you have now to work with, to add in anything else that you need in a design instead of it having being taken up with a wall on a jacket. So.
Right, and I would say, the typical range that people are coming to you and you're finding solutions are in 1, 2, 3 thousandths of an inch. Is that a standard range of kind of finished wall thickness on the product?
That's right. Yeah. It's as everybody says, you can never go thin enough on this, but when you look at the flexibility that we've achieved with this PEBAX, people are finding that they can go with a thicker wall. It adds durability. It adds a lot of other characteristics that they need in a thicker wall. But they're able to get that now in a much thinner wall than they had previously with the reflow process or extrusion, anything like that.
Very good. Well, thank you. I think it's, the pictures on screen actually show, I'm sure, thought-provoking, and we've seen some really interesting applications. let's move on to Darren quickly. Darren, thanks for hanging out.
No problem.
Let's talk before kind of doing a review of everything you guys do. Can we talk about the advantages of using a laser cut hypotube in a delivery system? What are the trade-offs? What are we looking at?
Yeah, with a laser cut hypertube, you do get some key advantages. You get some pretty high kink resistance because of the nature of the hypertube. The cross section of it and the hoop stress in there helps to retain a good kink resistance. The other thing is obviously ovality along the tube. Even if you're going around some quite tortuous curves and things like that in the anatomy, it does retain pretty good ovality. So that gives then the design engineer a lot of space in which to have a security that they can deliver a device down that central lumen. High torque resistance, high torque is also a big advantage. Depending on the type of laser cut pattern, if you do an interrupted spiral hypercut, you have a good chunk of spine of stainless steel running down that, solid steel running down that shaft, which does give you pretty high torque outputs at the distal end.
I think this sort of starts to illustrate more of what you're talking about.
Yeah, no, it does. So what you're also able to do with the laser cut tube is along that shaft, you can put other features into the tube. You can put in small tab-like features, windows, drill holes there for attaching a PTFE liner. And you can also vary the type of pattern that you're using along the tube to get a different flexibility and different stiffness from the proximal end to the distal end.
Very good. Yeah, I think the evolution of these patterns over the last number of years has been incredible. And I remember when we first saw the first of the puzzle piece designs come out, it's just brilliant to see all of our customers creatively take this technology and come up with new applications, new ways of using the opportunity. And as you said, this interrupted spiral cut pattern, answers some of the issues with, that the coil had created.
Yeah, it's probably, I would say it's probably the workhorse pattern that we use at Excel. It gives a good degree of flexibility. If you want more flexibility, probably go into a radial cut slot pattern, but there then becomes some disadvantages there with kind of pushability and retaining some, it's very difficult in handling unless it's right at the distal end. Some other advantages with laser cutting a tube along that whole length is that you can do things like the laser ablation. So we can control the focal length of the laser into the tube wall and create knurl or radial rings for overmolding or UV bonding. And they do really make an impact because it gives a nice keying feature there on the OD surface of the hypertube.
Got it. So I was going to ask you about applications that might combine multiple technologies and take advantage of what you guys do at Excel. So it fair to say that not everything is either an EDM process or a laser process or a conventional micromachining process. There are challenges that bring these together.
Yeah, absolutely. And I think that's one of our big selling points. It's one of our USPs is that we've got 4 or 5 good, solid, traditional machining capabilities from laser tube cutting, flat laser cutting, traditional CNC machining, 3D printing, and EDM wire and sync machining, where we're not a jack of all trades, but we are literally under one roof, a master of all those trades. We've got several engineers who have got, plus 20, 30 years experience in those capabilities. So we can look at a different component and bring the best solution to the customer to that, you know, and then that can follow on to the hypertube itself. You know, if we need to laser weld something onto the OD of the tube, that can be a real benefit for the design engineer as well.
Okay. One thing that we hadn't really talked on before, and I did just want to pull in, was the metal 3D printing. You see that capability interacting with shaft development, or is that sort of a separate class of product or of a challenge that you're seeing from customers right now?
For a hypertube, I've not got many applications of 3D printing, but it wouldn't surprise me if tomorrow I've got something in my inbox from one of the DSA reps asking for that. But we do several products for customers where we 3D print quite a small micro machine part, maybe down to less than 200 thou, down to maybe 80 thou in size. And we laser weld that to a 200-300 millimeter long tube, and it's for an application for a sports med application. So we are seeing 3D printed components being used more and more in medical device applications. And if we need, we obviously got other capabilities that we can make sure we get that final component the customer's looking for.
Yeah, I think that's exactly what I was wondering is if you saw, for instance, tips for fluid flow or, you know, sensors or other things being fabricated that way.
Yeah.
I guess it's just always a trade-off between doing that way or with a good, fast, conventional machinist, right? Yeah. The one advantage with the 3D printing, and the other area where we've got a lot of strength is our EDM machining, and that can be we've turned that very much to high volume manufacturing, you know, 30, 40, 50, 100,000 units a year. So that's seen as a capability that maybe was used only for tool making, but we've very much, we've developed that for high volume medical device manufacturing. Very good. And then the final thing I'll highlight just here, and feel free to riff on it. You even, you know, show on this, you know, the PET outer jacket. You know, one of the things we'll talk about in the panel is how different companies work with partners and supply chain and other things. But you obviously don't make heat shrink, but you source heat shrink tubing and apply it, you know, where customers want it. On the other hand, you know, XL is also a supplier to other contract manufacturers, right, or customers directly. So, I mean, we are talking, I think, you know, one of the things we'll obviously our attendees know, right? There's a choice between design and make it yourself and build, right? And so we have, you know, some of our customers want to build these products and assemble them themselves, and then we're supplying materials, and others want to, you know, get as complex and complete an assembly as they possibly can. Any comments on that?
Absolutely. We've got several, you know, we supply both some of the very large medical device companies, the top 5, and we're just, you know, supplying them components, which is fine. We've got some great contract manufacturing partners that we are supplying sub-assemblies, and to some degree we've become their supplier of choice for anything metal, because they feel they've got great confidence in XL. And yeah, and then we've got some smaller companies that we deal with, OEMs, where they say, hey, we'd like you to make that whole kind of sub-assembly. You source the materials, you bring it together and put it through your Class 7 clean room. So yeah, we're humble enough to deal with everybody, Barry.
Very good. All right. Well, thank you, gentlemen, for a great conversation and for all the work that you put in. And to our attendees, I really appreciate you taking the time to do this today. Please do follow up with us on anything specific. Again, you can either get a hold of us through the DSA website and just send us questions with what you need. Talk to you soon.